Okay, so today we're going to talk about properties of logarithms. And some of these you will probably recognize because they have some analogous properties when it comes to exponents. But before we get started, I want to remind you of a few quick things about logarithms, all right? So if we have something where the log's base is 10, we can write that without the base. We can just say that that's the log of that thing. So log base 10 of x is equivalent to the log of x. When we have a base of e, we can also rewrite that with a different notation. We can say that that's the same as the ln of x. So log base e of x is the same thing as ln of x. And that's how you'll see it on your calculator. When we have a log with a base of something, in this case 2, then we're taking the log of something with an exponential base of 2. So the logarithm's base is 2 and the exponent's base is 2. These two things cancel out, the log base 2 and the 2 base of the exponent, and we are just left with whatever that exponent is. And so that is true here too. Ln of e to the 9th, well, that's really log base e of e to the 9th. And those two things cancel out and we're just left with that exponent of 9. So those are just quick reminders of some of the things that we see when we are talking about exponents. All right, so we're going to start with what's called the product rule. And you've seen the product rule before. The product rule talks about what happens when we've got the product, we're taking the log of a product. Well, it's the same really thing that's happening here. Do you remember when you have an exponent with a base of b raised to the m power times the b to the n power? That's the same as b raised to the m plus n power. Well, the same thing happens with logarithms. We're going to take this and we're going to say that this is equal to log base b of m plus log base b of n. Okay? So we're going to use this property, the product property, to simplify these four logarithms. We're going to break them into pieces and simplify them a little bit. So the first thing we would do here is say, well, this is the same as log base 5 of 7 plus log base 5 of 3. Notice we have a product, so we can take those factors and separate them into separate logs with that same base as where we started. Okay, so the next thing we're going to do is this one, log base 9 of 9x. Factors here we can break into separate logs. They're going to both be log base 9. And then we've got a 9x here, so we can break it apart. Log base 9 of 9 plus log base 9 of x. Now, we are done breaking it apart, but now we can simplify this, right? Because log base 9 of 9, well, what is the power here, right? That's just a 1. So I can say that this is 1 plus log base 9 of x. So we're going to do the same thing here. Log of 10,000x. Factors. Break them into two pieces, okay? So log of 10,000 plus log of x. All right, so this is, I can't do anything more with this, but this one, think about this. What is the base here, even though we can't see it? The base is 10. So what power of 10 is 10,000? Well, that's easy. Just count the zeros, right? So this is actually 4 plus log of x. Okay. Last one. ln of 12e. Okay, well, let's break this into the two factors. ln of 12 plus ln of e. Can't do anything with this one, but this one, what's the base? Base is e. So it's log base e of e, that's just 1. ln of 12 plus 1. Okay, that takes care of the product rule. Okay, so now we're going to look at the quotient rule. The quotient rule is similar. Remember when you have two exponents with the same base and we're dividing them? What do we do with that? Well, we take those exponents and do what? We subtract them. All right? And that is the same as with logarithm. Okay, so if I have log base b of m divided by n, I can break that into two logs. And I can say, well, that is the log base b of m minus the log base b of n. Okay, so the top is positive, the bottom is negative. See, positive is the top one, negative is the bottom one. We'll use that a little more later. So let's take this one and break it apart. Log base 7 of 7 minus log base 7 of x. Oh, that log base 7 of 7, they've got the same bases. What does this end up being? Log base 7 of 7 transforms into 1. 1 minus log base 7 of x. All right, let's look at this one. Log base 4 of 64 divided by x. Break it into the two pieces, the division. Here is log base 4 of 64 minus log base 4 of x. Okay, now I think that 4 or 64 can be written as a power of 4. And what power of 4 is 64? That would be 3. So this whole thing can transform into 3 minus log base 4 of x. Log base or log of x divided by 1,000. That's just log of x minus log of 1,000. Probably need a new marker. All right, this one is good, but this one, what power of 10 is 1,000? Remember that trick? Count those zeros. So this whole thing transforms into just 3. Log base 10 of 1,000 is 3. And last one here, ln of e to the 5th minus ln of 3. Fantastic. What do we do with this? Get rid of what that common base is e, right? So e, ln of e, or really it's log base e of e to the 5th. That can transform into just the power, which is 5. Okay, fantastic. Rule is really the same thing as the product rule, but with a kind of a shortcut. So the power rule says that if I have an exponent like this, or a logarithm like this, log base b of x raised to the p power, I can take that power and bring it out here like this. Okay, so I can take that power and write it as, not that marker, write it as a coefficient to that logarithm, p times log base b of x. So that p comes out front and acts as a coefficient. So you can go either direction. You can bring it out here, or if it's in front already, you can write it as an exponent to the argument, either one. So this is very simple. All we're going to do is rewrite these so that the arguments don't have powers. Okay, so this one, easy. Take that 7 out in front, right? And we have 7 log base b of x. Next here, we can take this power of -6, bring it out in front. -6 times log of n, capital N here. All right, this cube on this y can come out front. So this would be log 3 times log base 9 of y. Oh, where's the power there? Remember, rational exponents are the same as radical. So I can take this radical and rewrite it. ln of the 5th root of x, that's the same as x to the 1/5 power. All right, so when I do that, I can now bring that 1/5 out in front. So 1/5 ln of x is the equivalent logarithmic expression without a power on the argument. So all of these properties are gearing us up so we can expand and condense logarithms. That becomes helpful when we're solving certain problems. And so we use these properties to actually take complex logs and make them into simpler logs expanded, or take something that has lots of logs with the same base and condense them into one. So we're going to start by looking at expanding logarithms. And when we do that, you'll probably be asked something like this: expand the logarithm as much as possible. Well, what does that mean? When it's asking you to take it and expand it as much as possible, you're going to want to make sure that the arguments of the logs have nothing that we've talked about. No products, no quotients, and no powers. Okay, so no products, no quotients, and no powers. Okay, so that is talking about whatever we're taking the logarithm of. In this case, we would be looking at x times y cubed. All right? So let's try that one. And when you are looking at these, you want to think to yourself, do I see products, quotients, or powers? I need to get rid of them. Okay, so do you see that I have a product? I've got x times y cubed. But I also have a power. I've got a cube on the y. So first, get and expand using the product and the quotient rule, if possible. And then deal with the powers. Okay, so let's take this and break it apart. We could say that this is the same as log base b of x plus because it's a product, right? Log base b of y cubed. Okay, so now I'm looking at those logs saying, I don't see any more products, but I do see a power here that I need to get rid of. So let's take that, bring it out front. Log base b of x plus, bring that 3 out front, 3 log base b of y. Okay, and so now I'm looking and I see no products, no quotients, and no powers, and so this has been expanded as much as possible. All right, let's look at this next one. How about let's look at this one? Okay, so we have, let's see, when I'm looking at the argument, I see kind of 3 pieces. Do you see them? Here's a piece, here's a piece, and here's a piece. Okay, so I see a product in the numerator. I see a quotient because I have a numerator and a denominator, and I see lots of powers. Okay, so let's break this up using the product and quotient rule. And remember I said that when you use that quotient rule, anything in the denominator will end up negative. All right, so let's take this 1, 2, 3 spots. We got 3 logarithms here. We can start with this step. Log base b of the cube root of x plus, what else is in that numerator? Log base b of y to the 4th. And then this is where it becomes negative. Then this is where it becomes negative, minus log base b of z to the 5th power. Okay, so now looking at these arguments, there's no product or quotient, no product or quotient, no product or quotient, but every single one of these has powers. We need to get rid of them. So I want to pull the powers out in front. Now this one is not written in power form, but do you remember I can rewrite this as a fraction exponent. That cube root of x is the same as x to the 1/3 power. So now I can just take all of these exponents and pull them out front. All right, so my final answer will be 1/3 log base b of x plus 4 log base b of y minus 5 log base b of z. Okay, and I'm looking and I see no products, no quotients, no powers, and I'm good. Okay, let's look at this last expansion problem. Log base 6 of 36 divided by the square root of x plus 1. Okay, so do you see products? I don't see products this time, but I do see a quotient, and this radical means that there's a power going on. So let's first break it apart into the two things for the quotient. Log base 6 of 36 minus log base 6 of the square root of x plus 1. Okay, so both of these things have something that I can do something with, right? Because I think you should recognize that 36 is a power of 6. What power of 6? And so this whole thing just transforms into 2. All right, now I want you to think about this one. We may take this in 2 steps. Remember that we can write a radical as a fractional exponent, log base 6 of x plus 1 all raised to the 1/2 power, right? And then what we're going to do is take that 1/2 power and pull it out front. So our final answer here is going to be 2 minus 1/2 log base 6 of x plus 1, okay? So we've expanded these logs using that power, quotient, and product rules. Okay, so we're going to condense some logs. Notice that in these cases, the logs have the same base. If they have the same base, we can put them together into one single log, which is often helpful for us. Okay, so we're going to use those properties, but we're going to use them kind of backwards. If you see a coefficiental log, we're going to create a power. If you see a plus sign in between logs, we're going to create something where the arguments are multiplied. If we see a minus, we're going to divide. Okay, so let's work these problems. We're going to start with this first one. 1/2 times the ln of x plus ln of y. Okay, so we're going to rewrite this as the 1/2 power of x. Okay, and how else can we write that? We can write that as a radical, right? So this is really ln of square root of x plus ln of y. Now, since we've just got those two ln's and we got a plus in between, we can write it as ln of a single log. So you're only going to write ln or log one time. And then we're going to multiply those two things together because I see that plus sign. And when you've got that single log and you've got everything in the argument, you are finished. Okay, so the next one, we're going to do the same thing. Only this time, we are going to divide. So let's move first this coefficient of 4 over here to the power of 4. All right, and let's move this coefficient 3 over here to the power of 3. And then let's rewrite it so it is one logarithm. All right, so let's look. How about this? ln of, and when we see this minus sign, we've got some division going on, so let's go ahead and create a fraction bar. Let's put this thing up top because it's positive. X plus 6 raised to the 4th power. And then we're subtracting this one so it becomes in the denominator x cubed. Okay, and we're taking that log of that whole thing. Now notice I've got a plus in there. I can't do anything with that. Remember, we've got a product rule and a quotient rule and a power rule. We don't have a sum rule, okay? So this is complete. Some of you might be tempted to try to break it apart some, but you can't. All right, let's try this one. We got a 1/3 on the outside. Let's go ahead and distribute it through, okay? And let's see, we'll start by just distributing. 1/3 log base 4 of x minus 1/3 log base 4 of y. All right, now let's take those 1/3 and let's bring them to powers of the argument. So this is going to be a 1/3 up here. This is going to be a 1/3 up here. So that 1/3 now, we can write that as a cube root. Okay, so let's do that. Log base 4 of the cube root of x minus log base 4 of the cube root of y. So now we're at the point where we want to write it as a single logarithm. We're going to take those things and put them together. 1 log base 4. You can write it one time, right? This minus sign means a fraction bar. The positive thing goes on the top, cube root of 4. The negative thing goes on the bottom. I'm sorry, that's the cube root of x. The cube root of y, okay? And we can leave it like this, or we can write it so that the radical, that cube root, is over the whole thing, x over y. Either one of those is fine. This is a little more elegant, but either one is actually correct. Okay, so let's move to change of base property. Change of base property says that I can take a logarithm with any base I want, log base b, of anything, and rewrite it with a different base, okay? Perhaps my calculator only does specific bases. Many of them are restricted to only doing base 10 and base e. If that's you, this is going to be especially helpful, because I can take this log base b of m and write it with any base I want. I'm going to call this new base, log base c of m and log base c of b. So now I'm writing it as a ratio of 2 logs with a new base c, whatever c happens to be. Okay? Notice that the argument stays on the top. This original base goes to the bottom. So this is a really handy formula, especially if we use it with the bases that our calculator likes. So what happens if I make that c a 10? Isn't that just log? So that would be log of m over log of b. Or perhaps I might like to think of it with a base of, instead of c, the letter e, or the number e, right? Isn't that the same as ln of m over ln of b? Okay, so all of these things are great to know. So what we're going to do now, we're going to take these and rewrite them with a change of base expression so that then you can put it in your calculator and check and make sure you can get the right answer out. So you want to be able to use your technology to get a good decimal approximation. So log base 5 of 400, this could be written with logarithms, with common logs, log of 400 over log of 5. And you can get that approximation out of your calculator, and we'll get it in just a second. All right, we're going to do all of them at once, all right? All right, let's do this next one. Okay, this time let's use natural logs instead of common logs. So we can call this ln of 63 over ln of pi, and we should get a good answer out there. So if I'm looking at this one, I could write it with either common logs or natural logs. Either one is correct. Let's try log of 19 over log of 0.1. So now you're going to take your technology and get a decimal approximation out. You're just going to crunch these values in your calculator. Take a second and do that, and pause the video and let's get some approximations up there for you. Now check your answers. You should get 3.723 if we go to 3 decimal places here, 3.619, and negative 1.279 here. Notice that we use approximation symbols here because it's approximately this. Your calculator didn't say exactly this, so we would use the approximation symbol. And what this means is if I took 5 and took it and raised it to this power, I should end up back at 400. Okay, so you can double check your answers that way. Take pi and raise it to 3.619 and you should get about 63 out. Are you going to get exactly? No, because why? Because we approximated here. It's not exactly this in the calculator. All right, so that's it about properties of logs for this time, and I'll see you next time.